Okay, we'll get started. Um, so today we're going to introduce the basic formalism of the normalization group, and we're going to see uh, how it is so powerful and how it is able to go beyond the Kadanoff block spin picture that we've been using up to now. So I want to start off, though, by reminding you about where we finished last time. So last time we introduced what I think is the most important concept in the entire course, and that is the concept of scale interference. So do you need to move that chair? Yeah. So scale interference was the idea that scales that you thought could not possibly be important at the critical point or near or in any kind of phenomenon actually turned out to be very important. And so I want to go through that once again. It was something we talked about at the end of the lecture. So at the end of the lecture, I told you about the two-point correlation function evaluated at the critical temperature. So that's G as a function of wave number K, wave number just being the Fourier transform of space, evaluated at the critical temperature. And you can work out I'll show you how to do this later. We'll do dimensional analysis on field theory, and we will see that we can compute the dimensions of the two-point correlation function. And without any approximation, those dimensions turn out to be length squared. Okay, so that's the first thing. The second thing that I showed you was over here on the left-hand side. Over here on the left-hand side, I told you that at the critical temperature, the correlation function decays as a power law. I haven't yet proved that to you, but we will see it. And it goes with a power law with an exponent eta plus a d minus 2, where d is the spatial dimension. And we've talked a little bit about how that crosses over from the exponential decay of correlations for large distances. All right, so when I take the Fourier transform of that, you can all do that in integral, just take the Fourier transform. You will find that the r to the d disappears, and what you end up with is what I've shown over here on the what I've shown over here on the right. G of k goes as k to the minus 2 plus eta. That's how we define that critical exponent. And so what we're learning from this is that then if I took the dimensions of that, the dimensions of k are inverse length, it's just the Fourier transform. And so that says that the dimensions of the two-point correlation function at Tc is length to the power 2 minus eta, and not length squared. And so that is like, how's that possible? We violated dimensional analysis. So sometimes if people say at critical points, dimensional analysis gets violated, this is what they mean. So now let's talk about how we resolve this problem. So you could say, well, maybe the wave number isn't the only length scale in the problem. So what other length scales are there? Well, there's the correlation length, but the correlation length has gone to infinity. So that's no good. Then there's the system size, L, but that's also infinity because we're working in the thermodynamic limit. That's the only place where we see these non-analyticities. So it can't be that. The only length scale left is the lattice spacing, the ultraviolet cutoff in field theoretic language, the small distance scale. And so that's the only possibility that we have. That one is still non-zero. And so what we then must conclude is that if I look at g of k and t at Tc, that is going as a to the power eta times k to the minus 2 plus eta. And now with this combination, even though a is of the order of 1 angstrom, the correlation length has gone to infinity. And here we're looking at the long wavelength limit. So k in principle is going to 0. The correlation length has gone to infinity. This resolution, this hypothesis, then restores dimensional analysis. And it's really surprising that a tiny length scale cannot be neglected. And you might say tiny, tiny with respect to what? So what we're basically saying is that if I have the variable a over xi, and xi is a function of t, so I have that. If I call that variable, let's say pi1, what that says is that the limit as pi1 goes to 0 is a singular limit. And indeed, in the language that we used at the beginning of the class, this is an example of intermediate asymptotics of the second kind. And if you remember what I meant by intermediate asymptotics of the second kind, what we did was we wrote dimensional analysis of some function, some variable pi, dimensionless variable as a function of the other dimensionless variables in whatever is the physics problem that you're trying to solve. And if the limit of pi1 goes to 0 is smooth, then you can say that the dimensionless group pi is f of 0, pi2 up to pi n. So that was first kind. And if in the case that we're talking about here for type 2 asymptotics, what we said was that pi goes like pi1 to some exponent alpha 1 times f times a different function, let's call it f tilde, of pi2 over pi1 to some power beta 1 all the way up to pi n over pi1 to the power beta n, like that. And this is how we defined the type 2 asymptotics. So here, these pi's are the dimensionless groups. And the type 1 asymptotics is common sense. If a variable is small, just neglect it. And that's what you learned on your mother's knee. And type 2 asymptotics is if a variable is small, but it comes in a singular way, you can't neglect it, however small it is. And that is the basic problem that we're dealing with in critical phenomena. And this is one of the reasons why it took 50 years for people to develop the solution to the problem of phase transitions. Okay, so that's the concept of scale interference, and we first run into it most potently here in the problem of phase transitions. But in other contexts, this arises in fluid mechanics, it arises in continuum mechanics, it arises in evolutionary biology, it arises in fluid turbulence, it arises in electromagnetism, it arises all over the place. People didn't realize that this could happen until everybody was forced into thinking about this, mainly from the point of view of phase transitions. And the first examples of this came from phase transitions, and that was why it was such an important problem and why the Nobel Prize was awarded for the solution of it. The first examples of this, however, were not found in phase transitions. The very, very first example that I know of was found in looking at the dynamics of shock waves, particularly spherically symmetric imploding shock waves going in like this towards a point. And those shock waves also exhibit this phenomenon. And this was discovered in the years around about 1942 to 1944. And some of you might be able to think about the history and speculate as to what was the physical context in which this phenomenon was discovered. Okay, so now I want to talk about a final scaling law. So the next thing I want to talk about is the Josephson scaling law. So what we are going to do today is I'm going to tell you about a scaling law for the free energy density and derive what's called the Josephson scaling law. That's in section 8.2 of my book. The basic formalism of the renormalization group will be the main thing that we're going to focus on in today's lecture. Today's lecture is going to be one of the driest lectures. I'm going to take out a part of it that I think I don't need to say, so I'm going to, as an experiment, try to streamline it a bit to make it even more palatable. I want to try to explain to you the basic idea behind the normalization group, what is the novelty of it, and if I get to it today, the origin of singular behavior, but expressed in the framework of the renormalization group. So I've told you about the fact that the variable pi1, a over xi, is a variable that you can't really neglect. And what I want to do now is I want to talk about the scaling of the free energy itself. And so our goal is to, we're going to derive that by looking at the scaling of the free energy density. So let's go ahead and do that. So the place I want to start is reminding you that what we talk about is the singular part of the free energy. And I've always been careful to call it the free energy density because we're looking at the singular part of the free energy per degree of freedom, per spin or per unit volume or lattice height. The reason is because we know that we take the thermodynamic limit. We take the thermodynamic limit that takes the volume or the system size to infinity. We want that limit to be well defined. So we talk about the density because we know we need to take the thermodynamic limit. We know that we must take eventually the thermodynamic limit. And so in order to get something finite, we need to consider the free energy density. So the thing that we consider then is the singular part of the free energy density. And normally we know that this comes in the Boltzmann factors like e to the minus energy over kT and things like this. So we know that really the appropriate variable to be thinking about is the free energy divided by the free energy density divided by kT. And that then will be something that is a dimensionless quantity per unit length divided by sorry, this has let me just say it more correctly. This has the units of energy per unit length over energy, and so the dimensions of this are then L to the power minus D. Like that. Okay, and so then you might say, well, what is the length scale that we would use here? Well, the only length scale in the problem is the correlation length as a function of t, but we know that we also have to think about the singular part of it as well. So we might say that then L we should write as psi, and then maybe there's a correction which I'll call B1. And then maybe A over xi, and this may come in some singular way, something like that. So that would be what we would expect then, based on our understanding of the phenomenon. And the leading scaling behavior is this. And then this part over here is possible corrections to scaling. as t tends to 0. So let's just then look at the singular part of the free energy density. So what we then have is that Fs over kBt, what we expect then is as we are going towards the critical point, this is going to scale like the correlation length to the power minus d, but we know the correlation length diverges as we go towards the critical point, and so that means it's going to scale like t to the power nu times d, because the correlation length itself diverges as t to the minus nu as t goes to 0. So that's how the single part of the free energy density has to scale with reduced temperature. Now, that's fine, but it's nothing that we can measure experimentally, or at least not easily, but we can relate this to an experimental quantity. By differentiating with respect to temperature. And if we do that, if we differentiate twice, then we get the specific heat, the heat capacity per unit volume, specific heat. So let's just be precise. So to be precise, the heat capacity scales like t to the power minus alpha. That defines the critical exponent alpha that we've already met before. And the heat capacity itself, I can write as minus t d2 fs by dt squared. And everywhere that you see t, let me just remind you, by the way, t is basically tc plus t minus tc, and that means that I can replace t by tc into 1 plus little t, where little t is equal to t minus tc over tc. And so basically, for when I have a factor of t in the equation, such as over here, I have a factor of t on the left-hand side. To leading order, I can always just replace that t by tc. So what that means is that when I compute the heat capacity, if the free energy is going as t to the nu d, then when I differentiate twice to get the heat capacity, then what I end up with is that the heat capacity, which is going to scale as t to the power nu d minus 2, and therefore I conclude that 2 minus alpha is equal to nu d. And that is the Josephson scaling law. And this is important for the following reason. If I look at the left-hand side here, this relates thermodynamics. This term nu tells you about the critical exponent for the correlation length. And then unexpectedly, we have the spatial dimension coming in. And so if you just saw this, then you would already know that this means that critical exponent would depend on spatial dimension, which you wouldn't know before. And in fact, Josephson derived this in the 1960s. And I'll tell you a quick story about that. When I was a graduate student in Cambridge in the late 1979 to 1982, the renormalization group was just being developed in those days, and we asked our professors to teach us the renormalization group, and the head of the theoretical physics group didn't believe in some of the things that were going on with the normalization group and the epsilon expansion. This was my PhD advisor, Sam Edwards. So he said, no, we're not going to teach it. We don't think it's well established enough yet. Okay. Of course, a few years later, Ken Wilson won the Nobel Prize for it, but this was Cambridge in England. So then we decided, okay, fine, we will teach it to ourselves. So I started a self-help group of graduate students, and we gave ourselves the first course I ever taught on the normalization group then was that one that we all did spontaneously. And one of the things that we did was I said, well, why didn't we ask Brian Josephson, who is a professor in the physics department and a Nobel Prize winner for the Josephson effect in superconductivity. And he'd done that work when he was a graduate student, by the way. So if you're a graduate student, you can win the Nobel Prize, okay? He won the Nobel Prize for work he did as a graduate student. And so I asked him, will you teach us about your scaling law? And he refused. He said, well, my scaling law is not as good as the other ones. And I said, well, why not? He said, well, my one involves dimensions, so it can break down. And the other ones don't. The other ones are always exact. And so my one is not as good. And it was very interesting. He had no interest in the modern theory of phase transitions as it was being developed then. And in fact, the thing that he felt was a bug in his scaling law is, in fact, the thing that makes it so important. Now, when he derived it, he didn't derive it as in the way that I did, a two-line argument that you could do over your cornflakes and breakfast. He derived it as an inequality, a rigorous mathematical inequality, and those rigorous inequalities then turn out to be exactly satisfied at the critical point. So anyway, we will talk a little bit about the consequences of this scaling law later on. I want to show you another scaling law, the last one I want to show you, just for completeness, and that is related to this one. I just want to mention it very quickly. I don't know the name of this scaling law. The scaling law is this. I know from the static susceptibility sum rule that the isothermal susceptibility scales as T to the minus gamma. I know that the correlation length scales as T to the minus nu. And so what you can do then is you can work out, and if you want to try it, I invite you to try it for yourself. You can work out that gamma over nu is equal to 2 minus eta. And this comes from the static susceptibility sum rule. So you are invited to check it if you want. Okay, so now let's talk about the renormalization group. So the next topic we're going to discuss then is the formal theory of renormalization group. And we're going to ask, well, what is it that we need to do? And so up to now, we had Kadanov's block spins. And we had the idea that the Hamiltonian now is a Hamiltonian that depends on scale. So there's an effective Hamiltonian that depends on the scale at which you are looking at the system. And so now let's talk about, well, does this work or does it not work? So the implications of this picture. So the first one is that we have to look at systems as coarse-grained. And what we assumed is that the Hamiltonian for the coarse-grained system is of the same form. When I say this, I'm going to say this means of the same form. We just invented that terminology, is of the same form So the original Hamiltonian and the coarse-grained Hamiltonian are of the same form. That was the assumption that we made. Then we made another assumption. We assumed when we did this that the effective temperature at scale L was the original temperature times L to some exponent, which I wrote as YT, and etc. And those were the two assumptions that we made. I'm going to change this title here of implications. I want to change it to be assumptions. Okay, so those were the two assumptions that we made, and so this one over here, number one, this one is not correct. And this is the most important thing that we're going to figure out how to get this. So we will correct this assumption. And see what we actually can calculate. And the bottom line is going to be this. If you were just trying to calculate coarse graining, that's really, really hard to do. And even today, it's virtually impossible to do it for most systems of interest, even though many people try to use it. I've seen people writing papers on trying to coarse grain cellular, deep neural networks, trying to understand how neural networks work from the point of view of coarse graining. Those things, generally speaking, are virtually impossible to do. And what we're going to see is what the RG tells us is that we don't need to do it, in fact. So it's not necessary to compute this coarse graining in detail. And that's really very surprising, because I've just tried to convince you that we have to think of the system in a coarse-grained way, and that is absolutely true. But what turns out to be the case is that the behavior of the system is only dominated by a few terms in this coarse-grained Hamiltonian, and in fact we can identify what they are, and we don't need to even know what their coefficients are, because they turn out not to matter. So this is all going to be explained, and this is going to be a consequence of the idea of the new thing that we're going to be introducing in here is the idea of fixed points. And so that's what I'm going to be talking about very, very shortly. So that's the first assumption. The second assumption this one over here, this assumption, as we will see, is actually correct. So this does work, and it explains the scaling laws that we've talked about, but it doesn't compute what the YT is. So it is correct, but is unable to compute the actual value of these numbers that we introduced, YT, YH, and in general others that one might come up with in a more general problem. So we don't know how to compute those. And what we're going to see is that from the renormalization group perspective, what RG is going to show is it's going to show how to compute these objects. And we're going to see that these things are related to the behavior of certain types of transformation that I'm going to show you now, the normalization group transformations near the vicinity of a fixed point. And that is the most important part of all of this. The most important thing that Wilson introduced was this concept of the fixed point. And this concept of the fixed point is important for removing both of the deficiencies of the Kadanoff picture. Okay, so what is the idea? So the idea of the renormalization group is that we're going to allow, we're not going to make the first assumption. So we're going to write a more general assumption. So let me show you how we do that. Let's go back to formulating the Hamiltonian in a kind of space, which I will, as a physicist, loosely call Hamiltonian space. So what do I mean by Hamiltonian space? So what I do is I say, remember when we started this course, I said, let's think of the Hamiltonian statistical mechanics as basically being the sum of terms. And I wrote these terms in this way. I wrote things called coupling constants and things called local operators. And so the local operators were quantities that varied on the degrees of freedom, the SI, and then the Ks were the coupling constants that told you how important a particular local operator was. So these were the coupling constants. And then these are the local operators. And the local, because they are operators composed of the underlying degrees of freedom. So when we talk about a Hamiltonian space, what do I mean by that? So the idea is this: we think of the local operators as forming a kind of basis. And then we can think of the coupling constants as being some sort of expansion coefficients. And so what we then say is, well, I can make a space that looks like this. I can't really draw a high dimensional space, so you're going to have to realize that this is a projection of a high dimensional space in some way. So this might be the direction K1, the direction K2, direction K3, K4, blah, 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 Kn, something like that. So that is a space, and every point in this space gives you a value of the coupling constants. So if I choose this point in space, the point in this coupling constant space gives you the value of K1, K2, K3, whatever, all these different coupling constants. And so that is the sort of coupling constant space. And we might say start off with the, say, nearest neighbor Ising model. So it might be that theta 1 is defined to be SI Sj, and so then I have K1, which is the coupling constant for I and J being nearest neighbors, like so, and then I might have theta 2 is equal to theta 2 is whatever it is. Well, other local operators, but their coupling constants are all equal to 0. So basically, you started off with a particular point in your space which corresponds to your original Hamiltonian. So what happens? Well, now when I coarse grain the system, the new interactions are going to be generated. So the picture is that when we coarse grain, the form of the Hamiltonian can change. And we discussed that when we introduced the Kadlov's block spin construction early on. So remember, I gave you this example. So I gave you the example of a Hamiltonian with next nearest neighbor interactions only. And then what would happen is if I coarse grained this up to some scale, L, then I would create interactions between nearest neighbor block spins. That was the example that I already told you. And so what that means is that if the coupling constants start off as being zero, once I start coarse graining, they can change. So that means that if the coupling constants are changing as a function of scale, then I can ask, how do the coupling constants change as a function of scale, and what does that look like? So now the questions are, how do the coupling constants evolve as I change the scale L of coarse graining? And the answer is, well, let's just take up our picture of our coupling constant space, just like the one I have on the previous page, something like this. So these are the axes, K1, K2, K3, blah, blah, blah. And I started off now with my system at this point in space. That was the original Hamiltonian I gave you. Once I've coarse grained it, I've introduced new coupling constants that were originally zero, now become non-zero. So that means that this thing evolves, say, to another place over here, where now K2 and K3 and K4 are not equal to zero. And if I keep on doing it, I'm going to make some trajectory in this coupling constant space, or if you like, this Hamiltonian space like that. So the question is, we're now going to say, well, when I look at this picture here, I say, well, that's nothing to do with phase transitions. That's dynamical systems theory. Dynamical systems theory is take a bunch of variables, they obey dynamical equations of motion. Now look at what happens to the dynamics. So this then is a phenomenon that can be thought of as dynamical systems theory in Hamiltonian space. And so that's what we are going to do. So that is the basic idea. So, okay, so you say that just sounds like a really disgusting mess. Why on earth would you want to do that? Why would you want to make it so complicated? So, well, what we're going to ask is, if I look at this trajectory, what are we really doing? So in writing, so the question is, why? Why do this? Isn't it awfully complicated? And the answer is yes, it is awfully complicated, but something nice can happen. Okay, so let's think about what that might be. So I want to just make sure that everybody understands why I can think of this as a dynamical system. So I'm going to go back now and talk about this coarse graining in detail. So the next thing I want to talk about is, to be precise, about how we are coarse graining. And later, we're actually going to implement this specifically for the two-dimensional Ising model, and we're going to solve it by exactly this sort of the normalization group. So for now, I want to just give you the picture. So the basic idea is that coarse graining changes the value of the coupling constants. So you could imagine this happening as step one. You coarse grain by an amount L. Okay, that's the first step. Now I've done your Kadanoff block spin construction. Then you say, well, that was so much fun. Let's suppose we've done that calculation. Let's suppose we say, well, that was so much fun. Let's do it again. And then you say, well, that was great. So let's do it n times. Let's do it again. So the result of doing that is that I've now coarse grained by L times L times L, blah, 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 which is L to the power n. So you can think of each of these steps of coarse graining as being places in this trajectory. So then the idea is that you can think of the trajectory as something like a fictitious time. Okay, so each coarse graining step, iteration 1, iteration 2, iteration 3, each of those steps, this time is like the step number. So it's a discrete set of steps. So the total time is something which we can call tau. That's going to scale like L to the power n after n steps, and we can think of the effective time variable is kind of like the logarithm of the scale. So we will see that the time variable is like a logarithm of the length scale. Okay? So, and we'll see that explicitly. So far I've just shown you what it means by looking at the picture on the left. Now I want to show you what is the magic ingredient of the renormalization group. So RG consists of the following steps. Step one is concretely construct Kadanoff's block spins. And I'm going to show you a way to do that in real space soon. Okay, so that's the first step. And this is basically the elimination of degrees of freedom on a scale lambda. So basically what that means is that any Fourier components greater than 2 pi over lambda, those are eliminated by the averaging, by the coarse graining. They are eliminated, leaving only longer wave, length Fourier components. And there's many different ways that one can implement this. So we talked about this conceptually in the following way. We said, well, just think of your system as being like this. Here's your lattice. Here's your microscopic lattice. And now we're going to coarse grain it into little blocks that we drew like that. That was our Kazanov block spins. And you can certainly do it like that, but it's not very well controlled. And so, in fact, there's multiple ways to do this. You can do this in real space, which we will do. You can do this in Fourier space, which you have to do by Feynman diagrams. We'll do that too. And there's other ways that one can do it: real space, Fourier space, other techniques such as decimation and other things like that. And you'll get an example to do that in one of the homeworks. But all of them have in common that they're eliminating long wavelength degrees of freedom. So basically, the upshot of doing step one is that the result of this is that I've made a mapping. I've made a map from the original coupling constants to new ones. And so when we talk about the renormalization group, what we really mean by that is a renormalization group transformation. And what that is explicitly a map of saying, take a vector of all the coupling constants after I've done this coarse graining. Let's suppose I've done it. That is going to be defined in terms of some nonlinear transformation that depends on scale, acting on the original coupling constants, k, like that. And so this thing here is some nonlinear function depending on L, depending on the scale. And in general, and L, of course, is greater than 1. And in general, this is a very, very complicated thing to construct. So if you ever go to a seminar and it's a theoretical condensed matter physicist giving a talk about renormalization group, and it's full of Feynman diagrams, all sorts of approximations and stuff like that, and your head is spinning, all you have to remember is that all of that is just somebody trying to tell you what is this function R sub L, and trying to construct it in some approximation scheme that works. Okay, and we'll talk about why you want to do that in a second. But for now, the hard part of the normalization group, the part that looks very confusing and blows people's minds, is the calculations that you need to do in order to construct this. Okay, and those calculations are frequently not systematic, and yet they still work to some extent, and we'll talk about that later on. But that is the part which is a difficult calculation. Now, what I want you to know is when you're seeing that, that's not the important thing, even though it may be the thing that pays the salary of the theoretical condensed matter physicist. Okay? The real important thing is what you do with the result once you get it. So for now, we're going to focus on what you do with this renormalization group transformation once you've got it. Okay, so now I want to make some comments about it. And the first comment is that this is a map which is many to one. And you've seen this before, but I want to now emphasize it in this particular context. So let's suppose I show you the following 3 configurations. So here is configuration 1. Here is configuration 2, and I haven't drawn it yet. Here is configuration 3. And let's suppose that in this configuration here, I have a spin down, a spin up, and a spin down. This one I have a spin up, spin down. And this one I have a spin up. I don't know, something like that. Okay, so these are microscopic configurations. Okay, now if I coarse grain them, what am I going to get? So this one has got two spins pointing down and one spin pointing up, the one on the left. So the macro picture of this one is going to be, this is going to be a spin configuration pointing down. This one here has, in the middle, has two spins pointing up and one pointing down. So if I were to coarse grain that, I would get a spin that points up. And this one on the right has got a spin pointing down, a spin pointing up, a spin pointing down, and a spin pointing up. But if I coarse grain it, I will then get a spin pointing up. So this is the coarse grained picture. And where would that, what would be the transformation that would correspond to this? So this coarse graining is what you would get if you did a majority rule map. So what do I mean by a majority rule map? So I look in each block, and then I ask, are there more up spins than down spins? And if yes, then that means we say then we have a spin up, and if no, then we replace it by a spin down. And that's all it is. We just look at the majority rule, and that means that I drew my little blocks there. On the left-hand side, I drew my block spins with an odd number of microscopic spins inside them. We're going to do this explicitly for the two-dimensional Ising model later on. So that's the first point. That's an example of coarse graining. So the other thing that comes out of this, so that's comment number one. Okay, comment number two is that if I look at these configurations, so let me call this configuration number one, number two, number three. So my comment number two is that both configuration two and configuration three, those go into the same coarse grained configuration. Okay, you can see that they both give you spin up when you coarse grain. But if I told you, here is the coarse grain configuration, spin up, can you tell me what was the microscopic configuration? Well, you can't, because it could be one of those two. In fact, there's even a third one it could be. So what that means is that there are, in fact, in this particular case, there are three microscopic configurations that map into the same coarse-grained configuration. And so what that means is that when I look at the renormalization group transformation, it has no inverse. So what that means then is that you might think that this process of doing successive renormalization group transformations, successive coarse grainings, is a kind of group transformation. And it is. but it's a transformation that has no inverse. It's a group that has no inverse, and we'll see it's a group later on. But it's not really a group, it's a semi-group. So when we talk about the renormalization group, actually, we should call it the renormalization semi-group, because it's really a semi-group. So it has no inverse, okay? Now, this, there's a subtlety here for those of you who know field theory. In the field theoretic renormalization group that was invented most famously by Gell-Mann and Lowe in 1954, but earlier than that by Stuckelberg and Peterman and so on, there people were looking at just particular subsets of the parameter spaces for quantum field theory, and those renormalization groups do have an inverse. Okay, but the real renormalization group, the full renormalization group, the one that we're talking about here, which is due to Wilson, does not have an inverse. So we'll talk about that some more as well. So now I want to ask the question, well, why do we call it a group? So let's now ask what happens when we do repeated application of coarse graining. So we're going to imagine that that I start off with some degrees of freedom, some coupling constants, which I'll write as a kind of vector like that, and then I apply a renormalization group transformation of scale L1 to that, and then once I've done that, I've got the image of that transformation, which I'll call K prime. So that is one renormalization group transformation. And then I'm going to say, okay, now let's take that K prime, and now let's act on it by another renormalization group transformation of scale L2. And we're not asking, how do we do the calculation? How do we do the coarse graining? How do we construct the renormalization group transformation? We're not asking that yet. All we're asking is, we know conceptually what it means. Let's ask what happens when we do that. So when we do that, then we're going to get an image of that, which I'll call K double prime. And so this K double prime then is the action of the renormalization group transformation at scale L2 acting on the renormalization group transformation scale L1, or acting on my original coupling constants. Okay, so this sequence of actions of this coarse graining transformation is what then drives the coupling constants to change, and that's what leads you on the left here to making a trajectory in this coupling constant space. Now, we're going to ask very specific questions about what that trajectory looks like in just a minute, but that's what we're doing here. So once we've done this, after I've got this scale up to K double prime, by how much have I coarse grained the system? Say it again. Right. So here we've coarse grained by the amount L1 times L2. Okay. So remember that, because later on we're going to see that this effect is the origin of why the effective temperature at scale L goes like the original temperature times L to some power y sub t. So that was the thing that we couldn't explain before. We're going to see that we actually can explain this functional form because of this group property, and we're going to talk about that in a few minutes. Okay, so next thing I want to ask is, we're doing all this coarse graining, and so it's kind of like, well, okay, so what's the point of all this? But then you might say, well, let's think about this for a minute. At the end of the day, what we want to do is calculate the partition function. And if we wanted to calculate the partition function, we should ask, well, does the partition function change when we do the normalization group? How many people think it changes? You know the answer, so don't. You don't know the answer?
I mean, we earlier assumed that H changes form.
Right.
So Z is written as e power minus beta. I'm assuming that's the answer. That's the reason.
Right. So, right. So I'm rich, right?
Yeah.
Yeah. So I'm going to saying the Hamiltonian has changed, and so therefore the partition function is e to the minus beta h, integral that, and therefore the partition function is changed. Okay. So let's think about whether that is really correct. We're going to see. Let me just see how far ahead. What we're going to see is that that's not quite correct. Okay. Now the reason is this. Just to tell you in advance, when we're coarse graining, we are changing the order in which we do all the averages in the partition function, but we are still doing the partition function. So even though we're changing the variables in the Hamiltonian, we're also changing the names of the variables that you're doing the integrals over to get the partition function. And those things will end up canceling out. Okay, and I'm going to show you that next. Okay, so what you said is exactly what most people would say. There's nothing wrong with it. So I want you to realize that what we're doing by the normalization group is we're kind of reorganizing the way that we calculate a complicated partition function, a very complicated many-body problem. And I still haven't yet told you in detail the thing that makes it tractable, but we're getting there. So the next thing we want to talk about then is the behavior of the partition function. We need to understand this, and we're going to just understand this in general terms. We still haven't talked about what happens when we're close to a phase transition. I haven't mentioned the word phase transition once yet this lecture, okay, as far as I know. So everything we're talking about now is just an alternative way of doing statistical mechanics, which Boltzmann could have come up with, or Gibbs or somebody, but they didn't, as far as I know. Okay, so let's talk about what happens to the partition function when we coarse grain. That's the question, and the answer is it doesn't change. And remember, I've drawn this picture for you several times before in this class. It doesn't change because I have this picture. Here's thermodynamics. Here's e to the minus beta f. Over here is the trace over all the spin degrees of freedom of e to the minus beta times the Hamiltonian. And then somewhere in the middle here is some functional integral of some Landau free energy that depends on some macroscopic order parameter. And all I'm doing is I'm changing the variables that I'm using to describe the system. But at the end of the day, I still have to be able to compute the thermodynamics. Okay, so let's go through this just a little bit more carefully. So here we go. So we're going to define the partition function of n spins as a function of the sets of coupling constants k. And I'm going to write this. If I don't do this, I'm going to get the wrong answer because I'll get minus signs messing everything up. So I'm going to call it, I'm going to define the partition function as trace e to the h, like that, where trace is over the microscopic spins. And so note here straight away that I've absorbed, for convenience, a factor of minus beta into my Hamilton. Okay, so I'm going to do that for now. So then my partition function is just trace e to the Hamiltonian. The free energy per degree of per degree of freedom I'll call G k, and that's going to be defined as 1 over n times the logarithm of Zn of k. So I've got n degrees of freedom. I have a whole bunch of coupling constants. I take the logarithm of the partition function. Because I've taken all the factors of minus beta into the Hamiltonian, then the free energy is just the logarithm of the partition function. So I can not have to worry about factors of minus beta. And so the free energy per degree of spin is just the logarithm of the partition function divided by the number of degrees of freedom, degrees of freedom, n. Okay. Okay, so that's just just some cosmetics. Now, when we do a renormalization group transformation, this reduces the number of degrees of freedom by factor L to the D. Okay, so then once I've done that, then what I have left is then I have n prime degrees of freedom, and that is the number of degrees of freedom I originally had divided by L to the D. So you might say that if I started off with my microscopic spins, I goes from 1 up to n. By the time I've done my coarse graining, I've got some coarse-grained microscopic spins. I'll label them with capital I, and this capital I goes from 1 now to n prime, which is n over L to the D. And my Hamiltonian has gone to a new Hamiltonian, which now is a function of n prime variables as opposed to n variables. And those variables are my coarse-grained variables, which I'm calling Si prime. So that's what we're doing when we're doing a renormalization group calculation. So what does it mean mathematically? Well, what it means is this. If I start off with my original Hamiltonian with n degrees of freedom, then it depends on my coupling constants k, and it depends on a bunch of k's, and it depends on my microscopic spins Si, like so. Then what I do is I take the trace over my microscopic degrees of freedom, but I'm coarse graining. I'm not doing the full statistical mechanics. So this coarse graining here, this sum is a constrained sum over configurations where I only include microscopic configurations that lead to a specific coarse-grained configuration Si prime. Okay, so let's unpack this. So the game is this. You tell me what is the macroscopic configuration that you want to achieve. So let's go back here to the screen on the left. I've got my 3 macroscopic configurations here. And let's suppose you say, I want to know what is the effective Hamiltonian that governs the coarse-grained configuration, which is this one, the up one. So that means what I'm going to do is I only know that the coarse-grained configuration is up. But there's 2, in this example here, 2 or 3, in fact, microscopic configurations that are consistent with it. So I average only over microscopic configurations that are consistent with the upspin, so this one, and I don't do this one over here. So this is a constrained configuration. And so what that means is that you, on the left-hand side, have to tell me what it is, what coarse-grained configuration you want. So I've got my K prime, and then I have over here my SI prime like that. So let's draw this carefully. So what I'm saying is you tell me what is your coarse-grained configuration. That's the thing that you see on the left-hand side. You decided you wanted to know the up one. So now, when I do this sum over here, this is a constrained sum. So we might say put a trace. Actually, I'll put it over here. A prime on this trace, just to let you know that this is a constrained trace. It's not the full trace that you would have if you were just trying to compute the partition function. So if I do this, the game is you tell me what is the SI prime. So you have to tell me what you want for this. So you specify the coarse-grained configurations. That comes into the that comes into the right-hand side because it comes in here. I have to choose microscopic configurations that will give me the coarse-grained one that I want. So I do that trace of e to the hn, so that's summing over a bunch of exponential factors. I'm going to get some awfully complicated function. And what is that function going to depend on? That function is going to depend upon the coupling constants k, because every term in here is a term of e to the k1 or k2 or k3, whatever it is, times some combination of the microscopic variables. So when I do those traces, I'm going to get some horrifically complicated function of all the k primes, and then I'm going to define that whole thing as being the exponential of e to the h prime like that. So this way of writing it defines for me what is the coarse-grained Hamiltonian. So this this step here, this process, this defines the effective Hamiltonian as a function of its degrees of freedom SI prime. That's how we define it. Okay, and then what use is this? Well, what use this is that if I want to say, well, okay, fine, but what is the thermodynamics? What is the Helmholtz free energy? Okay, I want to know that. My answer is, oh, well, that's easy. If I want to get e to the minus f over kbt, all I have to do is take the trace over my new degrees of freedom, SI prime, of my new effective Hamiltonian, E HM prime, as a function of its coarse-grained degrees of freedom. So that will give me the free energy, and now I have to do the trace over the coarse-grained degrees of freedom. So that's this multi-scale picture of what we are doing. Okay, so let me give you an example of how to write this out. So there's a formal way to express this. And that is using the language of projection operators. So I'm going to go through this very quickly. It's for some of you it will make sense. For others of you it'll confuse you. we're not going to use it other than the thing I'm doing now. So if you don't get it, if you think, well, why are we doing this? Don't worry about it. Some of you will want to think about it, but my guess is that most of you will not. So I'm going to go through this fairly quickly, but I want to use it to make an important point. So I'm going to write this formal relationship in the following way. So I'm going to say, well, if I've got this over here on the left-hand side, this formal way of doing this constrained sum over configurations, I've written it down in English. How would I write it down in mathematics? Okay, so the way I would write it down in mathematics, I would say the following. All I have to do is take the trace over my microscopic degrees of freedom. I'm going to have a projection operator that comes in here that depends on SI and SI prime. And then over here, I'm going to have e to the Hamiltonian acting on the microscopic degrees of freedom. So this equation is meant to be the same as this equation over here on the left with all those words. So let's see how we construct this operator. And this operator P, this is the thing that I'm calling a projection operator. And it's very simple. It's just equal to the value 1 if the microscopic configuration is consistent with the coarse-grained configuration. So you can see it depends on both the microscopic and the coarse-grained variables, and it's equal to 0 if not. Okay, so it basically is defined magically to just do what I've said on the left-hand side. So you might say, okay, well, okay, how would I write a formula for this? Okay, this is all like hand waving. What is the formula? So let me now give you an example. So what I'm going to do is I'm going to have Ising spins on a lattice, just as we had before, with spacing A. And then I'm going to define my renormalization group transformation to take blocks of size 2L plus 1 times A, where L is an integer. And this means this transformation has the property that then there is an odd number of spins in the block. So I'm going to use the majority rule coarse graining that I mentioned a few minutes ago. So my majority rule says then SI prime is equal to the sine of the sum of all the spins in the block of SI. And then because it's a sine, it's just plus or minus 1. So if there's more spins pointing up, I get 1. If there's more spins pointing down, I get minus 1. So that is how I define my coarse-grained variable. And my projection operator, and this is where I'm going to end today's lecture, the corresponding projection operator is this one. And the next time we'll unpack this, is the product over the coarse-grained lattice, a delta function, a Kronecker delta function of SI prime minus the sine of the sum of I in big I SI. And that's how I literally can write down this projection operator. Okay, so it's time to finish. So I'm going to stop the recording, and then I'll be happy to take questions outside. So let me just do that.